Okay, we are at the top of the hour, so I am going to get us started here. Hello, everybody, and welcome to Quantum Analytics webinar. I am Lauren Armstrong, Marketing Director for Quantum Analytics, and I will be your moderator for today's event. Today, we're going to explore the topic of gas analysis by mass spectrometry and show you how to take your engineering experiments to the next level with the power of real time. Before I introduce our speaker, I want to give you a super quick overview about quantum analytics. We specialize in gas chromatography, liquid chromatography, elemental analysis, and molecular spectroscopy based solutions. Our company's history is deeply rooted in our 30+ year channel partner relationship with Agilent Technologies. And since then, we've also had the fortune of adding additional premier partnerships to our catalog. This includes Bruker, Frontier Labs, Marks, Activated Research Company, Elementar Americas, SciTech, as well as Diablo Analytical, who are going to be joining us today. Whether you are looking for a single instrument or looking for a complete workflow comprised of instruments from different vendors, our team has you covered. We offer cross platform integration, application support, flexible financing and leasing programs, as well as an array of certified refurbished instruments available for quick delivery. As I mentioned, we'll be joined today by Dr. Terry Ramus and Dr. Scott Hine, both principals of quantum analytics partner Diablo Analytical. Dr. Terry Ramus will be the primary speaker, and Dr. Scott Hine will be available to answer questions during the Q&A. Over the last 35 years, Dr. Terry Ramus has done research in gas phase analytical techniques with an emphasis on applications of mass spectrometry and GCMS for the industrial and engineering sectors, including applications related to process measurements for engineering experiments such as catalysis, reactor performance, yield optimization, and scale up. Dr. Scott Hine has focused primarily on scientific software development for data acquisition, instrument control, and data analysis. These efforts have produced software solutions like Diablo's Easy Reporter software, which has become an industry standard for natural gas analysis reporting, and the MS Sensor software, which provides a process analysis interface for real time gas analysis by mass spectrometry. So as a registered guest, you're going to receive a link to this recorded webinar in your email when it becomes available. We've reserved about an hour for this webinar, including Q&A. Type your questions at any time into the text box in the question module that you see on the right side of your screen. We're going to be keeping a roster of these questions and pose them to both Dr. Ramus and Dr. Hine at the end of the webinar. This ends our introduction, so without further delay, I present to you Dr. Terry Ramus.
Well, thank you, Lauren, and thank you everyone for joining today. We want to talk about the background on how you might choose a particular analyzer for a particular process application. And in the end, the emphasis will be gas analysis in real time by mass spectrometry, and I'll explain the details behind achieving that. The 5000B RTGA mass spectrometer is the basis of the ultimate solution we'll be showing you, and we'll show why real time would be important. Real time is looking at a video of your process rather than looking at a photo of your process, a snapshot. We'll show the design features that make this work specifically for this particular analyzer, and we'll show some applications and how the method development would proceed. The emphasis here is on a dynamic R&D engineering development environment. So it's a system that allows you to have lots of flexibility and to quickly make changes. So whenever we're going to look at a process, we should begin by being process centric. And so the whole idea is we have the process on the right and we have all the knobs and switches. That's obviously the old days. And the question then is, I can't see in my process. I've got knobs that I can turn. which do I turn and how much? So in more modern times, we continue to try to put eyes into the process so that we can see what's actually happening in our process and then make adjustments as needed. So one common way of looking at a process is with gas chromatography, which is a very powerful technique. Um, it gives you lots of great speciation. It can be, set up for good detection limits as well. The issue and the problem and the limitation of gas chromatography is depending upon the GC you choose, the analysis can run in the period of several minutes. It could be up to 20 minutes, or they could be as short as maybe a couple of minutes. But in between the GC injections, you're not getting any information in your process and you're not able to see in your process. So by today's standards, GC is considered slow and not real time. So if you take an RTGA or a mass spec appropriately designed, now we can acquire data on the single second time frame. And so now, as you can see in the graph there, we can see in real time how various parameters and various chemical concentrations are changing within our process. And therefore, in real time, we get a video instead of a snapshot, and now we can more easily see what's happening and then possibly make changes in our process. So by modern standards, this is considered fast. So if we step back again and look at our process, um, the question is, can I see clearly? And usually people, when you're picking an analyzer, you want to pick one that is specific for the analytes that you have in question. In other words, you don't want interferences to cause problems with actually seeing your components of interest. So that's the first question. Have I chosen an analyzer that really can see the components I want to see? And the next big question that comes along and oftentimes is not able to be achieved is, can I see the amounts? In other words, is it a quantitative analyzer, or does it just monitor trends? And then finally is the question of real time, or what is happening now, and how can I see quickly what's going on? So we're going to show you today how to look widely and clearly for many components and have them be able to be specific due to the power of the mass spectrometer with good detection limits and a broad dynamic range, and to do it quantitative and to do it in real time. So this is how to actually very clearly be able to see your process in real time. So, again, if we were stepping back and looking at our process and what analyzer do we want to look at, it would depend upon the process and the goals, but GC or gas chromatography is very powerful, but it's very pokey. Optical spectroscopy is okay if you happen to be able to see the specific components you're looking for, but optical spectrometry is blind to a lot of the components that you may want to look at in many processes. Infrared spectrometry is powerful, but calibration to get quantitative results is complicated, and detection limits for infrared tend to be not great. So if you take mass spectrometry on its face, it's looking, at the mass to charge ratio of a fragment from each component. It's linear up to four orders, into four orders of magnitude of dynamic range, and it can operate very fast in the single second acquisition timescale. So if you're looking and getting a data point every second, you can see up to 3,600 times per hour with a mass spec, where maybe you would get a data point between 4 and 10 times per hour with a gas chromatograph. And oftentimes both techniques might be complementary to looking in detail at a process. And as I mentioned, the mass spectrometer can see almost everything. The exception is if you have two components that hide under the same mass. but we can see small things all the way down to hydrogen. We can see inert gases, we can see organic components, and we can see certainly up beyond the range of anything that would be considered a gas. And it can be done with this system quantitatively with a simple calibration. So now let's talk about how we achieve all of these goals with this particular device. And here's just a review question for you to consider. And that is, just think about this. How fast is real time? And if you just consider, maybe you have a window, you're looking outside of your office and you're watching cars go down the street or something, how quickly do you have to be able to see with your eyes a new data point before you consider it real time? Um, if you were looking at a TV or screen and you had an update every second, that would seem slow. But certainly, if you had an update every minute or every hour, that would not be real time. So the answer is it needs to be at least on the second time scale to give you a video of your process versus a photo snapshot. So this is the 5000B real-time gas analyzer. There's a picture of it there. You can see that it's a modified Agilent mass spectrometer. And then of course the software, I'll show you more. You can see the screen in the back. It can be on a laptop. This whole thing can be on a cart. Um, but the software then also sits on top of the Agilent software. We're able to achieve this because we are Agilent channel partners, and so we work with Agilent on making this available as a partner product. Our TGA has then several features. There's the real-time software platform, and with the mass spec, you can still use it as a GCMS. If you attach the mass spec to a GC, the software is there and ready for that. Or if you fairly quickly remove the GC and put the RTGA gas interface in place, then the RTGA software takes over. We have 4 different sampling design interface designs, and as I mentioned, it's designed around the Agilent 5977 mass spec, the current product. We have an application builder, so you can quickly go from concept to acquisition, and we have a simplified calibration software with pressure compensation that I'll go over in more detail. And we have what we call the dual mode capability, and I'll describe how that expands our linear dynamic range. So these are 2 of the interface options. The way to look at these is if you look at high flow option number 1, your process sample would enter through the T, the green T. You can see process gas in and process gas out. And then the bypass pump, you can see the sample flows through an orifice to a cross, and then the bypass pump sucks the sample across an orifice. And we'll discuss how important the particular orifice is and how this all works in detail. But then the sample moves across a second orifice through the isolation valve and goes to the mass spectrometer on the left-hand side. And this is continuous, and you can look at a wide range of pressures and temperatures in attaching to your process. Now the number 2 option for the interface, the fast response option, it functions the same as the first, except that it is a lower volume device, and that allows very fast response times on the order of a single second. In other words, from the time a new sample enters that T until the time you see it on the screen is approximately 1 second. In the previous case, it might be more like 3 seconds. The third option for an interface is a direct flow option, and this is if you want to minimize the removal of gas from your process, microreactors, for example. And so you can have a small 16th inch stainless steel line with a flow that's in the maybe 8 mils per minute total flow, and that flow would go through and across the orifice. It would be again drawn in by the bypass sample scroll pump. And then the fourth option is because of the design here and because mass spectrometry is a vacuum technique, we can do vacuum sampling. Now, the vacuum sampling may be down to 20 torr, so we're not talking about extreme levels of vacuum. But those are the four different interface options, and they're very easy to change and configure between the orifices if you want to change them or if they get plugged. It's just a VCR fitting that you simply spin open, put a new one in, and retighten. This is what the screen looks like on the software. And so rather than having a gas chromatography type software, we have a process uh, view in which the x-axis is now the time frame of your experiment. So we have different components you can see in the top right there. There's methane, nitrogen, oxygen, etc. And each of those represents that particular component that you're looking at, and it's based upon a particular mass to charge fragment that's from that component that's being looked at by the mass spec. This is a modern software platform, and it's very flexible and very easy to use. So you basically, very simply with the screen in the top left, pull up your method, a data file, and press acquire. And then you start to see the acquisition, which is zoomed in on in the lower right. And so this might run for an hour, it might run for many hours, it might run for several days. Those are common within how our customers use the system. But then while it's running, you can pull data from the system and look at it with the sensor, MS Sensor Data Viewer. And you can zoom in on different components. You can eliminate some or look at all the components at once. And then you could take a region of that data and you can do a calibration during the run. And that's what we show in the lower right there. And you can then update your calibration during the run. Calibration is very straightforward. It's an external standard calibration, which we're used to, and you can do an external standard calibration, and then you can apply it to that component in your sample matrix that's coming out of your process. Um, a very important thing about this system, which is not common for analyzers that you might look at a process with, is we're able to set up a method so that we're quickly alternating on the second time scale. And so alternating acquisitions would be done with one of two different acquisition methods. In the example shown here, the first acquisition would be set up with a hydrogen tune capability. And that hydrogen tune allows you to see down to mass 2.0, also to see helium, lower mass components. And then the second acquisition would be a standard tune for looking at all the components up to high mass. This mass spec goes up to very high mass, very much higher than you would typically go for most gases. And so we're able to, within a single method, get both types of acquisitions in a single run. The second use of this is a way to extend the dynamic range of the analysis. In mass spec, there's something called SIM, or selected ion monitoring. And this is used to sit on a particular mass to charge of interest for a component for more trace detection. The problem is if we're in sim mode, we typically can only look at a couple of components with high sensitivity, and we typically have the instrument configured so that a matrix component would be far too intense and it would saturate the mass spectrometer. So what we can do is, again, on the second time scale, we can we can alternate between a scan mode, which looks at all detectable components. So for example, we can see from 100% down to certainly the mid part per million, depending on the component, sometimes lower. And then what we can do is alternate back and forth with a sim acquisition that focuses just on some lower concentration components, and in that case is not looking at a matrix component. So this is a way, as I say, to extend the dynamic range, get sort of the best of both worlds, the 100% matrix view as well as the lower level detection within a single acquisition, within a single method. Just as an example, obviously we get these run charts, and this shows an example of a breakthrough study from an adsorption bed. And so you can see that we have a series of sulfur compounds, and you can see that around 9 minutes that the challenge gas is introduced into an adsorption bed. And the objective of this, of course, would be to look for the point at which the bed starts to become saturated. And you can see that around 26 minutes, the signals start to increase as the bed starts to reach saturation. So this is just one of many examples. You can look at catalysis, you can look at syngas, you can look at really essentially any stream that is in the gas phase. We don't want to have any two-phase composition. We want to have only gases, and we achieve that through heat and through appropriate pressure control and sampling system design. So in order to make all this work, it turns out that one of the most important part of the system is obviously besides having a very capable mass spectrometer, very reliable, very reproducible, and sensitive, we need to have an interface, a gas interface that's properly designed. Most of the time when processes are hooked up, or much of the time what happens is too much sample is provided to the mass spec, and so the mass spec is always working really on the edge of saturation. So we're going to heat the interface, we're going to make sure gas goes through it, but to make the mass spec work at its best, we're going to reduce the sample pressure, because mass spec is a device that runs at 10 to the minus 4, 10 to the minus 5 torr. So somehow we have to very reproducibly and consistently reduce the pressure. And we also have to reduce the sample flow. Mass spec is very sensitive, so we're going to end up with a very small amount of sample actually ever reaching the mass spectrometer. But we need to do this continuously, and we're going to have to dilute the sample. And then mass spec, unfortunately, it is not only a concentration detector, but it is a pressure detector. And so if we have pressure changing in our process, that induces changes in what looks like the signal level. And we have to deconvolute the pressure changes from the concentration changes. And then, of course, we need to have our system, our response be matrix independent. We want to be able to calibrate with a gas mixture in, for example, helium, and we want to apply that external standard calibration to our process gas with all the matrix present. So if we look at that, the interface that I showed earlier, let's take a view as to how the sample flows through the system. So you can see process stream in the upper right, going down to the vent. And that's just potentially you want a large flow, possibly 100 mils a minute, liters per minute, whatever it might be. And it's just flowing past the analyzer. The analyzer then, with the bypass scroll pump, draws in a few mils per minute across the first orifice, and it drops down to a tenth of a torr from 5 psi, from 100 psi, whatever it might be in your process. And you can see that in the cross on the top, that device is a capacitance manometer that's doing a very accurate measurement of the pressure. And we're going to use that to compensate for pressure changes later. But most of the sample is going to go out the bottom of the cross into the bypass sample scroll pump. And that's how we're reducing the pressure, but that's how we reduce the concentration. So finally, a small amount of sample goes across the second orifice, 50 microns in this case, and into the mass spectrometer, which is at maybe 10 to the minus fifth torr. So this is the key design, and the key is that it's very reliable, and it turns out to be matrix independent because of the pressure regimes that we are at in each step of the process. So this is an example. The red arrows sort of remind us where the sample's going. Most of the sample is coming in and going out the bypass pump, and a small but reproducible amount of sample is going into the mass spec through the second orifice. We sometimes call this a conductance split. Similar concept to splits we might run into in lots of instrumentation, but in this case, in mass spectrometry, we are dealing with conductance. So now we have to examine the pressure problem, potential problem at least. If we, in the upper right, have a process that has some pressure fluctuation, which is typically or often there can be, pressure fluctuation. The challenge is that in mass spectrometry, that pressure change for the sample will translate through the device, through the interface, and will result in a pressure change inside the source of a mass spectrometer. And if you have a simple capillary interface, whatever kind of interface you have, this would be the case unless you had instituted some pressure control in your process stream in. And sometimes that pressure control can limit the actual sample in terms of how it reaches the analyzer. So what we do is we measure the pressure at the cross with a capacitance manometer, and we ratio the current pressure to a pressure at the time of calibration. And using that mathematical equation, which is embedded in the software, you can use it or not. And you can, in fact, change that equation if you want to have something, model it and have a more detailed equation. That is how pressure compensation is achieved. You can see the molecules in the source, the black dots in the blue box. You can picture that if you have a change in the pressure and you now have fewer black dots, then the ion beam going through the source of the mass spectrometer is then going to generate less ionization. The opposite, of course, would happen if you had, a higher concentration due to a higher pressure. So the flow characteristics are that the sample comes in where the big black arrow is in bulk flow, goes through the T, and a little bit of that sample is brought across the first orifice, the 30 micron orifice. And because of the degree of pressure change, it induces what's called a sonic flow or a sonic expansion. And it ends up with a pressure that's low enough that within the distances that the molecules are traveling, that the molecules do not interact with each other, collide, and so forth. So once we go across that orifice, we freeze the sample composition, and then the sample does not undergo further changes. That's what provides the matrix independence part of the analyzer. And then, of course, we go across the second orifice, and you can see that the concentration is reduced, both due to the conductance split and due to the pressure change that we actually have in the source of the mass spectrometer. So we can then use a simple external standard calibration because of the matrix independence capability of this. Simple gas standards in, say, helium, but then do a robust quantitation so that we can look at the components that are in our process stream. So let's just think about a question a key question based on what we've been discussing over the last few minutes. What are the requirements for matrix independence, for an analysis that's independent of the matrix? In other words, the concentration or the response factors for the analytes do not change due to a change in the matrix. Okay, so we have to account for sample pressure changes during the run. We have to prevent molecular interactions after the sampling, that's after that first orifice. And we have to freeze the sample composition so that the sample composition does not change based on the matrix. And of course, the answer is we have to have all three of those, all of the above. We have to compensate for the pressure, we have to prevent intermolecular interactions, and we have to freeze the sample composition in the interface. Now, let's say that in your application, you're going to go to a higher pressure. So in this case, in the upper right, you can see that we have a 200 PSI sample. What we can do is we can decrease the diameter of the first orifice. And so in this case, we've gone from 30 microns to 25 microns, and that's simply by spinning a VCR fitting open and putting in a 25 micron orifice. And at 200 PSI across 25 micron orifice, we still reach 0.1 torr. So the rest of the system works the same, even though your sample pressure is actually higher. And then, of course, this would be a vacuum, a subambient example, in which we're at 500 torr. So in this case, we could increase the diameter of the orifice from 30 microns to 40 microns. And again, the pressure would be about 1/10 of a torr in the cross, so the rest of the system then works in the same fashion. And of course, if we wanted to focus exclusively on some more sensitive or lower level components in our sample, we could increase the diameter of the second orifice, in this case, from 50 microns to 350 microns, and really allow more flow of sample into the mass spectrometer. So this is how you can easily manipulate and optimize the interface for your particular application. So if you go for higher sensitivity using the orifice approach, the larger orifice, you will not be able to monitor your matrix components. If instead you maintain with the 50 micron orifice and use the dual mode acquisition with SIM scan, then you can extend the dynamic range, continue to look at your matrix components in scan, and look then with better sensitivity at your lower level components with SIM. So there's two different strategies for looking at lower level components. The normal, most common mode to start with is we call the survey mode or normal sensitivity. In this setup, it's very difficult to do anything to damage the analyzer. You can adjust your process, and the analyzer is really able to handle a wide range of pressures and concentrations. So this is the mode that we normally recommend that we start out with first. So let's think here a little more closely. How can the sensitivity of the RTGA be increased in process monitoring? Okay, well, one idea is we could increase the the EM voltage. That's the electron multiplier, the ion detection, okay? That's like turning up the gain. Now, the downside of that is that if you just turn up the gain, you're going to increase the signal, but you're also going to increase the noise. So typically, you don't win with that. So, so you don't get any additional signal to noise by increasing the EM voltage. We can increase the size of the MS orifice, and we just went over that. That's one option, and we can get much better sensitivity, but we lose the ability to look at matrix species. The second option is to incorporate SIM with scan in a fast alternating method acquisition. The advantage of this approach is we can look at the matrix components with scan and the lower level components with SIM within the same experiment and within the same method. Instrument, stability is important. We've just shown you a baseline here. It's a very stable instrument. If you're doing acquisition over the course of days, sometimes there will be some drift and you'll have to compensate for that. There are various ways of doing it, but one is to periodically introduce your calibration gas from your cylinder, and then to do an adjustment periodically due to drift. You can see here, what we're trying to show is a system response. And so up until just before 8 minutes, we had helium, going into the system. And then all of a sudden, just before 8 minutes, we turn on a gas mixture, and you can see the very rapid fashion in which the interface responds. And this is the standard interface option number 1, not the fast interface. And then we also have to look at what happens on the backside. And you can see there's 2 examples up above. So you can see that there's a little bit of a delay in the return to baseline of the total ion signal. And if you look at the orange line, it's almost entirely due to water. Most of the time, water is not a component we're trying to measure. Water can be problematic. The system can tolerate water because of the scroll pump. So for example, we can look at syngas and we can look at combustion gases, but quantification, water tends to get stuck and buffered essentially in the interface. So you can see that CO2 in the bottom right example, it has a very slight delay to return over argon. And so that is a little slightly more sticky than, say, everything else. And so that shows the water curve coming down in the top, and then the CO2 curve versus argon coming down. Again, the point of this, showing how quickly it responds to a change in sample composition, or switching from the front end of the process, the gas at the front end, to the product end, or switching to a calibration cylinder. So in this case here, you can see that we have a sample being introduced, and we're looking at CO, CO2, and methane, and then and that's 20% of each. And then we have an experiment where we're looking at air, and we're looking at oxygen, and we're looking at argon. And in that experiment, you can see the amber line is water. And so we want to remember that we always have a trace level of water present in the mass spectrometer at all times. And again, that's one of the things that makes quantitation of water more challenging by mass spectrometry. So let's look at method development. How did we decide which mass to charge values to choose? So, we could say, well, here we've got carbon monoxide, CO2, and methane, and we're going to use 44, 28, and 15. But how did we come up with those? Those are each ions corresponding, but how did we pick those particular ions? Okay, so we have something called the application builder. And so it's based on the NIST library. And you can see that we can type in, for example, methane in the search bar. And the fragmentation pattern that's shown there is for methane. And then we can add sequentially components to our method. So in the lower right corner of the table, you can see the ethane, ethylene, propane, propylene, and so on. Those are the components that we've added, and we've specified the approximate concentration. The software then goes out and looks at the ions that are present for a particular component. In this case, we're showing the methane. And you can see 16 is the highest, but it avoids choosing 16 because there would be an interference with oxygen. So the software recommends 15, which is essentially the next highest ion for methane that does not engage in an interference with another component. So this makes it much easier and quicker to take a new application, put a new method together, and then we're able to actually quickly make a method out of it, which I'll show you in a minute. So in this case, 28 for CO, 44 for CO2. Now you can see there is a slight interference between carbon dioxide with CO. So it would depend a little bit on the relative concentration of both of those. And then methane. This would be the best choices for these three gases. If we look at all three of them together, this is what the spectrum looks like, the mass spectrum of the three components at 20% each. And you can see that the detailed numbers in the table show us what the level of overlap will be, if any, is going to exist. Here I show another example for ethane, ethylene, propane, and propylene. And we pick the software picks a particular ions here. You can override that and choose a different one. And then from that, we're going to now make the method. And that would be showing 10% each of those components, ethane, ethylene, propane, and propylene, again with what the level of expected overlap, if any, would be between different components at a particular mass to charge ratio. Okay, and so now, how do we avoid or compensate for ion overlap? Well, we could use different ion fragments for separate analytes. And yes, if that's possible, that is the first thing to do. Use a high resolution mass spec. That would be a possible way to go, but it would be more expensive and is much more limited in availability. So that's a way of saying this is not a high resolution mass spectrometer. This is a single unit mass resolution device. The other example is by removing overlapping analytes from the sample. Well, that'd be great, but it's not always possible. But for example, if we're looking at a syngas and we want to measure carbon monoxide, then we might design our process so that we use argon as a purge gas in the system versus nitrogen, because carbon monoxide and oxygen and nitrogen, N2 and CO, both generate a signal at 28. So that would be an example where we might actually adjust or remove something that was in our experiment to avoid an overlap. So once we take our application method, we go to the application builder and put our application together. We then send it to the MS Sensor software, make an acquisition method, and then in the bottom right there, then we go into acquisition mode. So it's very quick to go from the application builder to the method to acquisition. Additionally, we can go into the method and further tune the instrument, tune the mass spec, or specifically specify sim versus scan. We can save the raw Agilent data file as well as the Diablo MS sensor data file. So there's lots of customization you can do beyond what the application builder generates for you. And and then while you're doing your experiment, at any time you want, you can view the real-time mass spectrum to see if something unusual were to appear, for example, in your uh, in your experiment. This is an example of a syngas experiment. And so just before 9 minutes, we go from the reactant gas, which has methane, and we put it through the catalyst bed, which converts it to hydrogen. And then over a period of 3 or 4 minutes, the catalyst bed then becomes exhausted and the hydrogen production drops, and we go back to essentially a methane composition. The calibrations are very linear with this interface and with the mass spectrometer, typically 4 orders of magnitude. And we've shown 4 examples here, including hydrogen. Hydrogen can traditionally be more challenging for a number of mass spec systems. You can see you get a nice linear calibration curve. So external standard calibrations, we have a wide dynamic range, linear curves, and we have matrix independence so that as you have changes in your process or as you go from calibration to process monitoring, you can use the same response factors, same calibrations, and we have pressure compensation. So this is a conclusion slide here, and then I'll hand it back over to Lauren. But the RTGA allows quantitative work, but it allows it to be done in real time. So you get essentially a video effect looking into your process. You can visualize what's happening in your process as if you had eyes in the process because of the speed uh, of that analyzer. And we can discuss applications with you. All right, Lauren, I'll turn it back over to you.
Fantastic. Thank you so much, Terry. And if you have a question for Terry about anything that he's presented today, about the technology or applications, go ahead and put your question into the question module that you see on the GoToWebinar control panel. And before we get to the Q&A, I wanted to share with everyone a webinar that we're going to be having next week. So on Wednesday, April 13th, we're going to be joined by our partner Frontier Lab to discuss rapid catalyst screening using the tandem microreactor GCMS system. So if you want to learn more about that, take a look at some of our other webinars. Definitely visit lqa.com/webinars to learn more. All right, let's dive into the Q&A here. So first up, how easy is it to change your RTGA orifices and maintain the MS interface?
Lauren, I think this is Scott. I think I'll take this one. It's actually very simple. I think Terry mentioned several times during his presentation that the orifice plates, they're simply VCR discs that have a laser drilled hole in them. And so you just close the isolation valve to the mass spectrometer, which protects the mass spectrometer, turn off the bypass pump to remove the vacuum from the interface, and then you just use a couple of wrenches to spin off the VCR fittings and replace the orifice with a new one, a different size, or let's say your orifice has become plugged. And then you just do the reverse process, spin it back on, turn the bypass pump back on, and then open the isolation valve, and you're ready to go again. So it's very simple to make that change if you need to.
Fantastic. Next question here is what process pressure ranges can the RTGA interface handle?
I'll take that one. This is Terry. So I showed an example where, maybe we had a sample that was at 10 psi versus 200 psi versus 500 torr. And so the answer to that is within a particular range of maybe 100 psi, you can use the same configuration of the same orifices. But if we went up to 200 psi, then what we would do is we would reduce the size of the first orifice so that we had a little bit higher pressure drop. And the goal is to maintain in all our applications about 1/10 of a torr in the cross. And then, of course, if we had a lower pressure, a subambient pressure, then we could change to a larger diameter orifice for that first orifice. And I gave the example where we had a 40 micron orifice instead of 30. And that was for the 500 torr sample application.
Fantastic. Next question here is, what is the advantage of the Agilent MSD used in the 5000A RTGA design?
Lauren, this is Scott. I'll take this one. When we were originally doing the development of the RTGA technology, we had many years of experience of trying to adapt different kinds of mass spectrometers to these process applications. And what we found is that the Agilent MSD is arguably the best benchtop single quadrupole mass spectrometer that's available in terms of its sensitivity, its stability, but it was designed for laboratory GCMS use. And so the whole reason we developed the RTGA was to take advantage of those attributes, but allow it to be used in a more of a continuous process mode. And our ability to do quantitation, our ability to do the alternating scan technology is all based on the capabilities of the 5977 MSD, the fast scan rate, the stability of the mass analyzer, the sensitivity of the system, all contribute to that. And when you compare it to, often people will use residual gas analyzers from the semiconductor processing or vacuum processing industry, and those are good instruments. They're a lot less expensive than the RTGA, but they don't have that same level of performance. And so, if you really need to do quantitation, if you need some of these advanced capabilities that Terry spoke about, it's really enabled by the capabilities of the 5977.
Fantastic. And I have another one here. What are the critical sample requirements for RTGA?
I'll take that one, Lauren. Well, the first and always critical requirement is that the sample must be, of course, a gas, and that means 100% of the sample must be a gas. And the most common culprit that we have to be careful about is, again, water. If we have a gas, but we have water that is condensing inside our sampling system, then that's going to cause all kinds of problems. The analysis will basically be invalid. So to deal with that, we must heat our sample system, heat tracing, that's common for people working in process analysis. So that's the first requirement, is the sample must be 100% gas. And then from there, depending upon the exact mixture and components in application, we would have to make sure that a pressure was correct, and we would go through and determine which ions, which fragments we were going to look at. in order to differentiate the components from the matrix. So that's the main requirement, is that it's a gas. Now, the other thing to mention is that some of our customers look at fairly corrosive species, acid halide gases, for example, and those actually work surprisingly well. But the bypass pump has to be a special scroll pump, and ultimately there's more wear and tear on the system. So if you have, say, 1,000 ppm or less levels of acid halide gases versus 100%, that'd be a very difficult application. So we do need to take into account the corrosiveness of some samples. So those would be the things to look at in evaluating whether an application is going to fit or not.
And Terry, I'll add one thing to your comment, and that is because our interface is based on an orifice-based pressure reduction technology, you do have to also be concerned about particulate or aerosols that could potentially plug that first sample orifice. And so let's say you're doing a catalyst experiment where you have catalyst fines that could get entrained in the sample stream. You need to have some sort of filtration that prevented that particulate from reaching and plugging the sample orifice. So that's something that needs to be dealt with in the design of your sampling system.
Fantastic. Well, I think that actually brings us to the end here. We're just at the top of the hour here. So I want to give a big thank you to Dr. Terry Ramus for presenting today's webinar, and for you, Dr. Scott Hine, for being available to answer our questions. Everyone who's registered for today's event is going to get a link to the recording once it's available, so you can share that with a colleague and rewatch some areas that you want to take another look at. That is it for us. So everyone have a great rest of your day, and we look forward to helping you expand the boundaries of your analysis. Thanks, everybody.